All right, I want to start off today's lesson by actually giving a warm-up question. And go ahead and try to expand the following binomials to the described power. So go ahead and pause the video right now and write out these expansions. So just kind of go through these. Anything raised to the zero power we know is always going to be equal to 1. A plus b raised to the first power is just itself. Anything raised to the first power is always just itself. A plus b squared. Now, this is the first time we actually have to do some multiplying. So we would say a plus b times a plus b would be equal to a squared plus 2ab plus b squared. Now, what about a plus b to the third power? Now, we could take our previous value, so a plus b squared, and also multiply it by a plus b. In any case, you would get a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, that's all pretty easy and pretty straightforward algebra. However, if I asked you to then go ahead and try to find something like a plus b to the 19th power, for example, it would be pretty annoying to have to multiply a plus b however many number of times. It would be annoying and pretty time consuming. So the question is there a way for us to expand a binomial? In other words, take a plus b and raise it to some power and do that a little bit more efficiently. And the answer is yes. It's called the binomial theorem. And the binomial theorem isn't anything particularly fancy. In fact, we can actually get a pretty good sense of what is going to happen just by looking at the series of expansions that we've come up with so far and see if we can start identifying some patterns. So I would encourage you to right now actually to pause the video and look at these expansions and ask yourself, do I notice any patterns specifically with the n value? If n represents our exponent value, do I recognize any patterns with the n value and what's going on with our expansions? So pause the video and see if you can come up with some of these characteristics. And if you've had a chance to actually think about these, then you'd see that these characteristics are listed here below. These are the characteristics of the expansion of a plus b to the n. And I won't go through them all, but hopefully you had a chance to think about this and you kind of see what's happening here. We notice that the number of terms is always n plus 1. We know that the powers of a are decreasing by 1, while the powers of b are going to increase by 1 term. And the sum of the exponents is always going to be equal to whatever your n value is. And kind of interestingly here, we also notice that the coefficients, right? If we go back here, let's say, take for example, the coefficients of our last expansion that we did, we'll notice that all of our coefficients here follow a particular pattern. And if you go to the last one, if we said 1a squared plus 2ab plus 1b squared, right? These coefficients here are exactly that of what we call Pascal's triangle. And Pascal's triangle, if you remember from your earlier math days, is effectively a mathematical pattern where every term that's generated is simply the sum of the terms or the values diagonally above it. So for example, this 5 here would be the sum of 1 and 4. This 4 here would be the sum of 1 and 3. So we can actually find all of the coefficients of our binomial expansion just by using Pascal's triangle. It turns out there's another way to also get these terms instead of just adding up the numbers diagonally above it, although you could certainly do that. But another option is actually for us to use what we call combinations. So we would go through this and we would say that this one value is actually 5, choose 0. And I'm going to write it in this form first, just so we can kind of see what's one way of writing it out. And so this 10 value we would say is 5, choose 3. This would be 5, choose 4. And trying really hard not to write the fraction symbol here, 5, choose 5. In other words, these coefficients or these values from Pascal's triangle can be used by something called combinations. All right, now let me break this down. So let me actually just finish writing this so we can get a sense that this is going to keep on going until you get to n minus 1 all the way to n choose n. So how are these coefficients generated? I call them combinations, and another way of saying them is to say n choose r, because what it's referring to is the number of ways that you can choose r elements from a set of n. So for example, if you had, let's say, 5 pairs of jeans that were sitting in a drawer and you were packing for a trip, and you could only choose 3 genes to take with you. The question would be, how many different ways can you choose three pairs of genes? Let's actually write it that way. Let's say 3 pairs of genes from the 5 that you have available, right? And another way of writing that mathematically would be to say 5 choose 3. So we would say 5 choose 3. That's notation. And another way of writing that is exactly what I have written up here, 5 choose 3. So what happens when you're doing 5 choose 3 or you're doing n choose r? Well, like I said, the notation can be kind of this parentheses with n over r, but it would be n factorial over r factorial times n minus r factorial. So again, if I just take this same value, so 5 choose 3, which is again 5 choose 3, what this would look like is the following. We would say 5 factorial all over 3 factorial times 5 minus 3 factorial. And if we remember how to simplify factorials, we would say we would just expand the larger factorial all the way until we get something that can be easily divided out. And now I see that 3 factorial would divide out. 2 goes into 20 10 times, and so this would all just be equal to 10. So what we're saying here is that every one of the terms that are in a row of Pascal's triangle, so when n is equal to 5, we start with this first term. And notice that the first terms in every row are always 1, because you're always going with the n choose 0. And n choose 0 is just going to be the value 1. Okay? So speaking of which, let's discuss some quick patterns here, things that we should know about n choose r. So again, we said n choose 0 is equal to 1. Make sure we understand why that's the case, because this would be n factorial over 0 factorial, which by definition is equal to 0, times n minus 0 factorial, which is just n. So these would just divide out and you're left with 1, okay, which I already have written there. So n choose n would be another one, right? Make sure again, maybe pause and think about why is n choose n equal to 1? Again, that would be n factorial over n factorial times n minus n factorial, which is just 0. So it's pretty much this, we're getting the same thing that we got before. This would just be 1 over 0 factorial, which is 1. So that would explain why all of these values, why the last terms in every row are always going to be equal to 1. And then a few others, n over 1, or n choose 1, excuse me, is equal to n choose n minus 1 is equal to n, and then finally n choose any r, again, is just going to be equal to the same thing as n choose n minus r. So I encourage you to stop for a second and think about why these are the case. Do the expansions if you need to. So to bring it back to my larger point about binomial expansion, let's actually do a problem now. Let's actually use what we know about either Pascal's triangle or using combinations that come up with the coefficients, and use the characteristics that we arrived at with our initial set of expansions up here, these characteristics, and let's try to use it to expand the following. Let's try to do 3x minus 2y to the 5th. Okay. Now, there are a couple ways to go about doing this, and one thing that I always encourage students to try, you don't have to, is to go through one set of rules at a time, meaning start with the coefficients first, and then do the expansion of 3x, and then do the expansion of negative 2y. So again, you don't have to do this, but I'm going to start with the coefficients. I notice that n is equal to 5 here, so I can either use Pascal's triangle or use combinations and start with what I know about the values in that row. So I would say 1, and I'm going to leave some space here, plus 5, plus 5, oh, excuse me, not 5, we're moving on to 10, I'm going to make some space, plus 10, plus 5, and then plus 1, okay? So kind of zoom out again so we can make sure all I'm doing right now is I'm just writing out spaces for the coefficients. Now let's move on to doing 3x. Well, if that is our a value, if that's our a value here, and I actually write it above so we don't get mixed up. If this is our a, then we're going to start with taking a and we're going to raise it to the 5th power. Then we're going to move on and write a to the 4th. I don't really like how that 5 looks. I'm going to fix that. okay? All right, back at it. So a to the fourth, a cubed, a squared, a, and then a to the 0, I'll just write it. You won't always have to write that, but just make sure we understand that's a to the 0. So now we've done our a's. And notice I've done something intentionally just to highlight a little bit of an issue here. When I'm substituting in my a now, I've got to make sure that I put in all of 3x. So I'm now going to go through and I'm going to rewrite this as 3x to the 5th. And you could have just done this from the beginning, but again, this is my very first time doing this problem with you all, so I want to make sure I don't get anyone too lost. So now I'm going to do all of 3x. And so I want to make sure that you understand when you're squaring it, you're not just squaring the x, you're going to be squaring all of 3x there. And so I can just clean those up. And this would just then be 3x to the 0, which again, we know is 1, but I'm just writing this out. All right, so now let's go and let's take care of, actually, let's try a different color. Let's do this next term. Now, what is b? Make sure that we understand, since we're subtracting 2y, this is plus negative 2y. So all of this is b. So we would say negative 2y to the 0 power to start. This would be negative 2y to the 1, because now we're incrementing our powers of negative 2y. So negative 2y to the second, negative 2y cubed, negative 2y squared, and excuse me, I should be going to the 4th, I apologize. There it is. And then this final one would be negative 2y to the 5th. All right. So that looks like a lot, but now we're going to clean this all up. Now we're ready to write our final expansion. So we're going to go through and we're going to multiply each one of these. So let's take this one at a time. 3 to the 5th power is going to be 243. And so we're left with 243 x to the 5th, and we don't have to worry about y because we're raising it to the 0 power. Now in the next one, we have 3 to the 4th, which is 81, times 5 times negative 2. So 81 times negative 10, that's going to be negative 810. X to the 4th, y to the 1st. Move on to the next one. I've got plus 3 cubed is 27. 27 times 10 is 270 times, now be careful here, don't multiply by negative 2. We're going to do 270 times 4 because it's negative 2 squared. And that should give me 1080 x cubed y squared. So I'm just going to go through the rest of these a little bit more quickly now. The next one, I know I have negative 2 raised to the 3rd power, so that's negative 8. So this all is going to be negative, so I have negative, let's see, 720 x squared y to the 3rd. This one would be plus 240 x times y to the 4th, and this would be minus 32 y to the 5th. So we have all that. So we're just going to go ahead and box all of that, and that is our final expansion, okay? So I go ahead and encourage you to now try the next problem. Try expanding this one. It's a little bit more complicated because now we have an imaginary and a radical in there, but if you take your time with it, you should still be able to work through it. And everything that we're doing right now is the binomial theorem. And so here it is. Here's the elusive binomial theorem. And looking at it just right now, if I had started off this lesson by just giving you that, I understand that that would look a little confusing, right? We're not exactly what's sure going on with this a to the n minus 1 times b to the 1. But now that we've actually done some expansions, we actually see this makes a whole lot of sense. We know that all of our coefficients here can be generated just by looking at Pascal's triangle or by using combinations. I recognize that all of my powers of A are going to be decreasing, right? And then all of my powers of B are increasing. And that's really all there is to it, and just really making sure that we're careful about taking the entire A or B term to that particular power. Now, I want to close this lesson by actually talking about what we say the rth term of A plus B to the n, the rth term. Now, R simply refers to the term number you want to find. The term number that you want to find. So I'm going to explain this concept as I go through this problem below. If, for example, I wanted to find the fifth term of 3x plus 2y to the 15th power. Now, note, that is a major expansion. That's a huge expansion. Like all of our coefficients and number of terms are going to be pretty large there. So I would have never asked you to fully just expand that, or would I? No, I wouldn't. That would be brutal. But I would expect you to be able to tell me a specific term in this expansion. So if I wanted you to find the fifth term of the expansion of 3x plus 2y to the 15th, make sure you recognize that r is equal to 5, right? The term that we're trying to find is our r value. And since we're expanding this to the 15th power, that is n. So when we are trying to find the fifth term here, what we would want to do in terms of our coefficients would be to say, I would want to make sure I understand that I'm doing 15 choose not 5, but actually 15 choose 4 for my coefficient. Now, pause and think about why that is the case. Earlier, when we were trying to find the first term, when we were finding the first term, we said n choose 0. When we tried to find the second term, our coefficient was n choose 1. The third term was n choose 3. So we noticed that the value that our R value that we are writing there, is always, the value here, n choose whatever we're trying to choose, is always one less than that term number we're trying to find. So we would say 15 choose 4 when we're trying to find the fifth term. Now from here, the rest of it is pretty easy. We're going to then take our A value. In this case, our A value is 3x, so 3x. And this part right here, don't let this confuse you too much. All we're saying is n minus whatever you said your r minus 1 is. And I just went ahead and distributed that negative, which is why it looks like n minus r plus 1. So that's not a typo. But if I say n minus the value of r minus 1, that's the power we're raising our 3x to. So we're going to say 3x is being raised to 15 minus 4. That's our exponent. Now going on, our b value is 2i. Our b value is then 2i, and we're raising that to the then fourth power. It's just the difference, whatever your r minus 1 was. So if we work through this, 15 choose 4 right here would look like 15 factorial over 4 factorial times 11 factorial. 3x raised to the, let me just clean that up here, 3x raised to the 11th power. Let's say 3x raised to the 11th power times 2y to the fourth power. A lot of this is something that you would just then do in your calculator, but your entire fifth term would be the following. Fix that 8. It's a pretty large term here. And that would be the fifth term of this entire expansion. Okay? And for this final problem, I want you to work through this on your own, but for something that might help you here is if I'm trying to find just the coefficient a, that is in the term ax to the 6th in this particular expansion of 3 minus x squared to the 12th power. First off, make sure we understand here what term number is this? And you might immediately assume and say, oh, it must be the particular term that is matching up with this degree here. But wait and think about this for a second. The only way that you could have x to the 6th must be x squared, or negative x squared, I should say, raised to the third power. And since this is our b value, right? If our b is being raised to the third power, all of this must be what? The fourth term. This must be the fourth term in our series expansion. So using that information, see if you can then find the coefficient, and you can check your solutions with what I have in Google Classroom.